So now I am very pleased to introduce Professor Todd Tripp, and he is a professor at UMass Amherst since 2003. And I noticed that he has been publishing papers on UV spectra since 1990. His first paper is using IUE data in 1990, and he has been doing absolutely crucial work on the CGM since then for more than 30 years. And I am very happy to introduce him as our first keynote speaker this week. Take it away, Todd.
Super. Well, I have to say, this meeting is really neat. I mean, don't get me wrong. I'd rather be in Santa Barbara than Western Massachusetts in the middle of January. But I'm quite impressed with what the meeting organizers have done, with all sorts of interesting conversations erupting online and virtual face-to-face conversations and videos, and it's just been spectacular. So I'd like to start by thanking the organizers for inviting me to participate in this workshop, which has been really fun, and I've learned a lot. So when I was thinking about how to put this talk together, I was reminded of an interview that Bill Moyers did with Jon Stewart of the famous Daily Show. And at the interview, at the end, Stewart said, well, you know, I just advanced the script. I have so many talented people around me. I just advance the script and they take it from there. So that's kind of the attitude that I adapted with this talk. Was I'm just going to put up some things that I find interesting. And there's so many really interesting and creative people in this workshop that I expect you all will take it from there. And probably my most important charge is to introduce this week's celebrity guest, which is, of course, Drummond Fielding, who will be doing the talk on Thursday. Drummond does great talks and is doing really interesting work. So I'm just trying to sort of set the table for Drummond. And along those lines, I have a pretty talented team that I've been fortunate enough to work with. Now, let's see, why is that not advancing my slides? Here we go. So I should give some of these folks credit. I will try to put up the names of people involved with specific papers, but I want to mention the COSPA team in particular because they've really helped out with many parts of the work of my own that I'll be talking about. Okay, so here's kind of a crude outline of what I want to try to talk about very generally. First of all, I'm going to make some kind of annoyingly didactic and sort of finger-wagging comments about the importance of spectral resolution. And then I'll try to do kind of a little whirlwind tour of different results related to multiphase gas. And my goal, if I succeed, is to bring up some of the challenges that are emerging from observations and maybe share some information about the kind of constraints that observations might provide for testing all the exciting theory that's rapidly developing in this field. So I guess, I feel like I don't really need to motivate this too much, but I suppose I should a little bit. I think it's pretty easy to explain the big picture importance of the circumgalactic medium and specifically multiphase gas. We can, for example, think of the Mahler and Bullock paper. One of my colleagues in the theory group in my department has steam start to pour out of his ears whenever I bring up this paper. But Ari was at UMass when he wrote this paper, and I think he kind of viewed it as a sketch of the broad ideas, and in that way it's a really nice paper. And one of the main points, I suppose, that this paper makes is that if you want to explain a big problem like the discrepancy between the observed galaxy luminosity function and expectations from CDM cosmology, well, you can invoke supernova feedback on the low mass end, and you can invoke AGN feedback on the high mass end. This is a little funky. I guess I need to swing this around here. But alternatively, you could explain some of this as the way that gas cools in a multi-phase situation. It's possible that much of the gas just is never able to cool and descend into the galaxy so that it can fuel star formation. So understanding exactly how gas cools and the physics that occurs as it descends into a galaxy is an important problem. Now, even if you do prefer, oh yeah, and I guess just so I don't catch hell from cats, I'll make sure to put up one of his famous papers, which is, of course, Duchamp's wonderful paper on how galaxies get their gas. And, if you have cold accretion and hot accretion and all sorts of things, that's likely to be multi-phase as well. But even if you do want to use feedback of some sort to solve this problem, you still have to understand how the outflows are launched and how the mass and energy couples with the CGM and the microphysics. And there's just a lot of different interesting theoretical aspects that almost always involve multi-phase gas in a very fundamental way. So my purpose here is to just show you a random sampling of observations, or observations that are interesting to me and that I know about, maybe. So starting with what I know about, I'd like to just make a quick comment about how theorists are working with ultraviolet and optical absorption spectroscopy. So what I've noticed is that many of the theory papers are trying to fit, for example, the COS halos data, which is total column densities, particularly of oxygen-6 and the circumgalactic media of galaxies. Now, the comment that I'd like to make is that that's a wonderful first step toward understanding the CGM, but there's a lot of information that's left behind if one is only working with these total column densities. These things have complicated component structure, and a variety of ionization stages are detected in the various systems, and there's a lot more that we can do. So this is nice, but I hope that theorists will start to dig into the data and look at some of the more detailed issues as well. And of course, along with this comes the responsibility for observers to explain the limitations of the data, the noise, the systematics, and so on and so forth. And I mean, I think theory really demands that observers do this because a lot of interesting work is racing ahead. And I sort of feel like we're getting behind a bit by not drilling down and working out some of the details that we can report from the observations. So I want to try to get into some of that today if I can. So one way to frame this perhaps is to just start with this simple question that Max and Peng posed: is multi-phase gas cloudy or misty? Now, to start, here are my somewhat snarky and finger-wagging comments. People are very excited about the cosmic origin spectrograph and the data that it's producing, and rightly so, because it's very good data, and it's opened up a lot of windows for observing the universe using ultraviolet spectroscopy. But it does have its limitations, and I just want to make sure that those are on the table here. So on the screen, I have actually an excellent COS spectrum. This has signal to noise of 40 to 1 per pixel. So this is about as good as the data get from COS. And you can see a couple of absorption lines here. You see we have a silicon 4 absorption feature with obviously multiple components. And adjacent to that, we have a Lyman alpha line from a different redshift. And again, we see, well, there's clearly several components in those absorption profiles. But we need to understand what we can learn from these data and what might be missing or not appreciated. Now, this is a little bit political, I suppose, but I think it's fair to point out that if we were to use a current X-ray spectrograph to look at these same absorption lines, we would see something like this. In fact, these are real data with about the resolution of current X-ray spectrographs. Future X-ray spectrographs will be better in terms of resolving power, but ultraviolet and optical spectroscopy will always be more orders of magnitude better than X-ray spectroscopy in terms of resolving power. So we should bear that in mind. We just need to understand what we can do and can't do with one type of instrument or another. But getting back to the cost data, we might be interested in this silicon 4 absorber. So we might say, well, let's compare it to the silicon 2 that we detect at the same redshift, and we might take a particular interest in this component over here, which seems to be lined up in these two ions of silicon. And we could do what I like to do, which is to convert the exponential absorption profile into a linear apparent column density profile, where we just take the optical depth in each pixel and use it to calculate a column density. This is advantageous because then we can scale different profiles to see how their shapes compare, and we can search for unresolved saturation, and these are just very handy things. So I'm going to show data like this quite a bit in this talk. So we might look at this and we might overlay the silicon 2 and silicon 4 and notice, well, this is a pretty nice component here. The two components have the same centroid. They seem to have the same line width. This seems like it's co-spatial gas. So we can take the silicon 2 to silicon 4 ratio, and we can pull up our favorite ionization model and figure things out. And this will just be swell. But here's where some of the unpleasantness starts to emerge. I have actually observed this quasar with a variety of instruments over the course of my career. This is H1821 plus 643. And I've recently observed it with the E140H mode of the Space Telescope Imaging Spectrograph, which provides a resolution of 2.5 kilometers per second. So it's interesting to compare what we had previously with STIS at 7 kilometers per second to what we get from COS. And so let me show that to you. So the top panel here shows the COS silicon 4 profile, and you can see the components, and you see, there's kind of a shoulder over here. When we get a little better resolution with the E140M mode, we see, well, this shoulder here actually resolves into two components, clearly, and we can see a lot of other component structure at other velocities. And then when we look at the same profile at 2.5 kilometers per second, we see even sharper, a little noisier this time because this is expensive and you can only get so much Hubble Space Telescope time, but we see sharper profiles, and we can see that we'll be able to do a better job of measuring the component-to-component properties with this high spectral resolution. But some of you out there might be saying, well, this middle panel is basically like what you get from Keck or the VLT with the Nichelle spectrograph, and it's good enough. And so, yay, Keck wins. We're all set. We don't need to worry about this business of higher spectral resolution. But let me show you some more of the data that we got with STIS. Okay, let's see. How come that's not advancing? There we go. So that's the silicon 4. You can also look at this silicon 2 profile and compare it to what we saw at 7 kilometers per second resolution. So what you see is that a feature that basically looked like one component, and I mean, maybe there's sort of a little funky thing here, but a lot of people would look at this and say, it's just one component, and fit it that way. When you look at it with the better resolution, it resolves into 5 discrete components, and those are real. We see them out in other species. We see them in overlapping orders. There's no doubt about the reality of those components. So spectral resolution is important, and we need to bear this in mind when we're comparing things, for example, in cost data. All right. So, for example, if we want to ask, is this a shattering cloud, which is an idea that theorists have become interested in lately, well, looking at it at 7 kilometers per second, we might not really get a lot of insight about that. But when we see this with better spectral resolution, it does start to look like something one might expect in this theoretical situation. All right, so why is this important? Well, let me push on and show something that pertains to the discussion that broke out over the weekend regarding metallicity in the circumgalactic medium. It was kind of an interesting conversation. People started to say, well, yes, it's, the metallicity, it's not meaningful. Who cares? You kids get off my lawn. But it's not just the metallicity. There's a lot of diagnostics in comparison of different ions. So for example, if we look at this particular example, we have a couple of oxygen 6 components down here. One component lines up beautifully with very strong H1, and the other oxygen 6 component, which has more or less the same oxygen 6 component column density, lines up with a much weaker and probably broader component. So there's a lot of stuff going on here from one component to another, and understanding that, it seems to me, is quite important for understanding the physics of the circumgalactic medium. Okay, so let me just make a few quick comments about what can happen if we're not careful with spectral resolution. So here's this same profile. Here's what it looks like at cost spectral resolution with good signal to noise. And you might say, oh, well, you know, I can see these inflections and these little minima in the cost data, so I would fit that with 3 components and I'd be fine. But what happens is that when you do that and you compare the results from the higher resolution data to the lower resolution data, you find, well, B values can be off by a factor of 2. Even column densities in one component or another can be off by a factor of 2. So that's troubling. X was saying, well, I don't think we can measure metallicity to a factor of 2. Well, we might not be able to measure column densities to a factor of 2. So that's an even worse situation, and one has to think about these things. Now, it usually turns out that the total column densities summed over these components are in agreement in the recordings with the different spectral resolution. But here's a more insidious problem. Oh, I'm missing a slide. Well, let me just speak the words. This is very good data. If we were to look at, say, just one exposure on this quasar, we'd have noisier data. And then this thing, which you can kind of see, well, there's 3 components. In noisier data, it looks like it's just one component. And it will look like the centroid is different from the centroid of the H1, and we end up reaching specious conclusions. Okay, so now I want to push on to looking at multiphase gas in a couple of different situations, and I want to start with gas in inflows. So inflows are kind of hard to observe because oftentimes it's hard to determine if the gas is inflowing or outflowing. In some situations, you can be confident that it's inflowing. For example, this is a paper by Kate Rubin, where it's a down-the-barrel observation of some galaxies where the kinematics of the absorption that's detected indicates that it's inflowing. So that's quite nice. But galaxies are faint, and sometimes there's limited information. So in this case, Kate was able to get magnesium-2 and iron-2. Well, it's hard to work with just magnesium-2 and iron-2. I know lots of folks here love magnesium-2, but this stuff is typically optically thin. There's a large ionization correction that's required. Magnesium can stick to dust. There's a metallicity issue. With only magnesium-2, it's hard to make a lot of progress on a lot of the questions that we're interested in. So we'd like to be able to get more information. So Stephanie Ho and Crystal Martin and her team have done some very nice work on evidence of inflowing gas by looking at how magnesium-2 velocities compare to rotation curves of edge-on galaxies. Chuck Steidel had done this some years ago, but this team has really followed up and done a wonderful job of sort of understanding the extent of the inflowing gas and its kinematics. And it looks like there is either evidence of inflow or a dropping rotation curve. I highly recommend these papers. And in fact, Stephanie has a nice little video up for this workshop where she's commented that one has to be careful about looking at where the magnesium-2 is with respect to the minor axis or the major axis, because sometimes there's confusion from magnesium-2 that's actually affiliated with other galaxies. So that's a nice little video, and it just illustrates how this workshop is really functioning in a wonderful way. And various teams and groups have done this. Dave Bowen has looked at multiple quasars behind NGC 1097, and his team also concludes that in absorption, they see a much larger H1 disk, which seems to be rotating in the same sense as the 21 centimeter and the starlight in this galaxy, and yet there seems to be requirement of an inflow component. So there's a lot of literature on this, and I apologize, I won't be able to mention everyone's literature, obviously, but lots of great work going on. But I think maybe the most interesting and informative place to learn about inflow is in our own backyard, because we clearly have some inflowing objects, and we have a lot of detailed information. So we have the high velocity clouds, we have the Magellanic Stream. And in this case, we can say without any doubt that these are multiphase entities. This figure from Sembach et al. Shows the 21 centimeter emission and contours, or the color scale. And then these little circles show detections of oxygen 6 absorption with the far ultraviolet spectroscopic explorer. And the color inside the circle indicates the velocity of the oxygen 6 absorption. Multiple colors reflect multiple velocities in different components. And we can see that the oxygen 6 absorption overall follows the kinematics of the 21 centimeter emission, even though the absorption is more extended than the emission. It probably tells us that these high velocity clouds have ionized envelopes, which isn't too much of a surprise. But we see a lot of things going on. And it's not just oxygen 6. We detect a lot of different ions when we look at quasars behind these high velocity clouds. So I'd like to now talk just a little bit about some of my own research. The high velocity community has a tendency to take this structure and snip out a big piece of it and only leave the kind of tip over here indicated in high velocity cloud maps like this. Now that's because this thing, which is unfortunately referred to as the outer arm, I think it can't possibly be affiliated with the true outer arm, doesn't quite deviate from rotation velocities as much as the high velocity cloud people would like it to. But I have argued that these things are related for various reasons. They have similar kinematics, they have similar metallicities, and they have similar distances. So this outer arm thing was constrained a few years ago by Lehner and Hauck, who looked at a star at a distance of 15 kiloparsecs and clearly detected that structure and absorption. And complex C up here has a similar distance from papers by Walker and Christom and collaborators. So these things are at similar distances. They're actually not that far away. Here's the spectrum from Nicola and Chris, and you can see that the outer arm absorption is quite nicely detected. It's interesting to note that there's an array of ions ranging from oxygen 1 up to carbon 4 that are kinematically aligned. And then there's also this high velocity part. I had dubbed this the high velocity ridge in a paper from 2003. This is also seen in 21 centimeter emission. So it does appear that the high velocity ridge, I should say, is in the complex C and also in the outer arm. So the kinematics are similar for both of these structures. So what I think is these are some kind of inflow in the Milky Way. They're not that far. They're probably now interacting with the ISM. They're decelerating, so the high velocity ridge might not have decelerated as much yet, and the lower velocity stuff is slowing down, and it's plowing into our ISM, and it gives us an interesting laboratory for looking at the physics of gas clouds interacting with a more dense ISM. So recently, as I said, observed this quasar H1821 plus 643 with this ultra-high spectral resolution with STIS. This cloud has some advantages over many quasar absorbers. Its location is constrained. So we have a pretty good idea about what the shape of the ionizing flux field and the intensity of the ionizing field will be. As Xiaowen pointed out, we often don't really know that in quasar absorption studies. And so we have an ambiguity. It's either the ionizing photon density or it's the particle density or both, and you can't really distinguish. But it's sort of nice in this situation because the ionization is reasonably well pinned down. Okay, so these are the data that I showed a few slides ago. So what can we do with these data? Well, if I can show one of these apparent column density comparisons, we see that the low ions compare pretty nicely, as we might expect, and we can look at ratios in different components and use that in ionization models. But it's also interesting to compare the low ionization absorption to more highly ionized species. So in these panels, black shows the silicon-4, and then I compare it to various things in the other panels, silicon-2, carbon-4, oxygen-6. And on the right side, it's just binned a little bit to show the features more clearly. So we can see, for example, in this component 3 and component 4, the silicon-4 and the silicon-2 profiles look quite similar, in fact, similar centroids and similar line widths at 2.5 kilometers per second resolution. On the other hand, the carbon-4 recorded at the same resolution, but with a little more noise, and the oxygen-6 with lower resolution, but still 15 kilometers per second, do not show those peaks, those clear components. These things seem to be smoother, broader profiles. And yet, there's clearly a relationship between the oxygen-6 and the carbon-4 in these lower ionization stages. When the lower ion stuff climbs up, so too does the high ion absorption. Okay, so what does this mean? Well, I think it's actually pretty interesting to explain how is it that the highly ionized species like oxygen-6 are kinematically correlated with low ionization stages like silicon-2. They have no business being together. The ionization to the energy to destroy silicon-2 is far lower than the energy needed to create oxygen-6. So what's going on? Well, let's just look at some more details here. We can run ionization models, so I've done that here. And it looks like there might be a need for a little bit of depletion in this particular component, because when I I try to fit everything as best I can, I find there's too much sulfur 2 in the observations. So if I adjust the model so that I get the sulfur 2, right, the purple here, then I would have the wrong amount of silicon-2 and iron-2. Well, that can be solved because silicon-2 and iron-2 stick to dust, and so maybe the silicon-2 and iron-2 are mildly depleted. But looking at this, we also show the silicon-4 in black, the carbon-4, and the oxygen-6. And as I said, we don't expect these things to have anything to do with each other, and yet the silicon-4 in particular has the same component structure in this component. So what's happening? Well, maybe it's something like what we talked about last week, where the gas is thermally broadened, and the things like carbon-4 and silicon-4 are broader than the carbon-4 and oxygen-6 are broader than the silicon-4 because of the different masses. So I tried doing that, and that works. You can, and of course, so if the carbon-4 and oxygen-6 are broader, they'll be more smeared together, and you'll get a broader profile. So you can fit the data that way, and you get fits that look just fine. But when you look at the ratios, it kind of falls apart. So the red here is what I measure for oxygen-6, the blue is carbon-4, and the black is silicon-4. And this is the temperature implied by the silicon-4 line width. And the ratios are all wrong. You could fiddle around with this, but it pretty much becomes unconstrained pretty quickly. So I'm not sure that just invoking thermal broadening of the lower mass species works here. So what's happening? Well, it's interesting to look at what these ionization models imply. Again, the ionizing flux intensity is constrained, so we get some constraints on the density. It looks like the density in the log is something like minus 0.7 to minus 0.3, total H column density about 10 to the 19. And so these things have a cloud thickness of 10 to 15 parsecs. Now, there are some systematic uncertainties. You know, the Fox et al. Model of the flux coming out of the Milky Way has some uncertainties. I haven't put all that in, But I think these give you a ballpark sense of the dimensions and character of these little clouds. And so a question for theorists is, does this look like shattering? Or does this look like precipitation or turbulent mixing layers or whatever you like? I think this is the kind of detail in the absorption data that I'd like to see theorists looking at more and more. And this might require simulation. So Cameron's demonstration of how to use Trident that might turn out to be very relevant. Okay, so maybe I should push on to some other things. Time is marching on. Multiphase gas and outflows is much easier to observe, and it's seen in all sorts of places. And of course, everyone loves the poster child M82, which is the Cigar Galaxy. Now the exploding Cigar Galaxy, it's seen in X-rays. We have dusts detected with Spitzer. There's molecular gas in the outflow. And of course, the famous optical emission lines that revealed this biconical outflow in the first place. So that's a pretty spectacular galaxy. There's a lot of literature. I'm not going to talk about it too much, but it's clearly multi-phase. One issue, though, is that emission goes as density squared, and it quickly becomes hard to detect emission as the density goes down. So often these things show us what's happening in the innermost CGM, but we don't really know what happens as the stuff flows out and away from the disk. Now, I would like to call out a paper that Edmund Hodgins-Kluck has put up that I think is a really nice paper on NGC 3079, which is another beautiful example of filaments coming out of the center of a galaxy. Looking at this image from Gerald Cecil, it doesn't look like it goes very far, so fine, whatever, doesn't have much of an impact on the galaxy. But what Edmund has shown in the recent paper is that this biconical outflow actually extends out to 60 kiloparsecs. So that makes it a lot more interesting. And also there's some interesting indications of multi-phase stuff going on. The edge of the X-ray wind is not the same as the edge of the far ultraviolet emission. And so, maybe this is a shell and you have X-rays filling the cavity and blah, 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 blah. This seems like a really neat example of a biconical outflow. Another example that people are loving these days, thanks to E Rosita, are the Fermi bubbles. And I won't spend a lot of time on this, but there is something that doesn't seem to be getting discussed, which puzzles me, because people will put up these Fermi bubbles and just start to talk about and measure them, or E Rosita bubbles, if you like. They're really the Fermi bubbles, excuse me. And what isn't getting discussed adequately, I think, is that this is the North Polar Spur, which we've known about for many decades. And the North Polar Spur is seen in polarization of starlight towards stars that are just a few hundred parsecs away. So the North Polar Spur part, at least, it seems to me, is not that far away. And so analysis of these E Rosita bubbles things should really make some effort to remove the North Polar Spur, unless I'm mistaken about this somehow. This might also be of interest, I suppose, to dispersion measure people, because it's a sort of pretty nearby thing, and it might show up in dispersion measure maps, even though we didn't see it in the discussion last week. I don't know. I haven't calculated that. Maybe it's not a very strong signal. But that doesn't reduce the interest in the Fermi bubbles. And of course, on the southern side, I have no explanation. It's just that I think the X-ray emission might be fainter than what it looks like when you just take a glance at this. It does look like the Fermi bubbles are not as extended as the E Rosita bubbles, at least on the south side there. So these are interesting things in a variety of ways. Here's 21 centimeter emission from, I don't know what's going on with my, I'm missing some of my references. I'm sorry about that. This is 21 centimeter emission, and you see these little clumpy things. And looking at these clumpy things in detail, molecular emission, carbon monoxide emission, is also detected. So these are multi-phase aspects of this very nearby, I'm sorry, my reference is up here. This very nearby outflow that, again, is beneficial because we can study a lot of detail. And for example, we can use ultraviolet absorption spectroscopy to kind of do tomography of this nearby outflow. And so this has been work led by Andy Fox and Rongman Bordeloi and their team. Rongman is on the panel after this, so maybe he can talk about this further. But they actually see redshifted and blue shifted absorption, which I think is believed to be the front side and the back side of the shell, and also the detection of the high velocity absorption or the non-detection depends on the location of the sight line with respect to the Fermi bubble. Outside of the Fermi bubble, the absorption seems to go away. Inside the Fermi bubble, there seems to be frequently detected absorption. So this is kind of promising. And actually, after this paper, there were several more papers looking at the bubble on the southern side. And so it's a nice set of work, and I encourage people to check it out. And maybe Rongman can talk about that more. Once again, we see this weird correlation of low ionization stages like carbon-2 with higher ionization stages like carbon-4 in the Fermi bubble absorption lines. So this has already showed up in 2 different places that, to me, suggests that there's something kind of interesting about it. Now, just quickly, our Milky Way has kind of a small town black hole and a small town outflow. If we look at something like Markarian 231, the nearest true quasar, we see much more dramatic outflows. And this is, again, a weird multi-phase situation. Markarian 231 is surrounded by an X-ray emitting nebula, which is roughly 50 by 50 kiloparsecs. And yet, Dave and Sylvain see sodium-1 absorption plowing into this stuff at 1,000 to 1,500 kilometers per second. And that's not just from the nucleus. There's also a star cluster away from the nucleus that has the high velocity outflow. So this brings up a question for theorists. How on earth does sodium-1, which has an ionization potential of only 5 electron volts, survive at these crazy velocities plowing through X-ray hot gas? I mean, I just think it's a really interesting question. Maybe you all understand this already, but it's an important clue about what goes on in outflows. Now, I've worked on this a bit with this team, and we've been focused on the nuclear outflow, specifically the broad absorption line outflow. We can see on the screen here that some of the iron 2 and magnesium BAL absorption features. We looked at this with COS in the ultraviolet a few years back in order to, of course, study the strong ultraviolet broad absorption features. And we were astonished and perplexed initially to find that there were no broad absorption features in the ultraviolet. Very strong BAL features in the near ultraviolet and optical, but in the far ultraviolet, they're gone. There's nothing there. There's continuum, but no BAL outflow. So what the heck? Well, the explanation to this is seen by looking at the spectral energy distribution of Markarian 231. In the optical and going into the near ultraviolet, it's very reddened, and it's basically what people now call a red quasar. But then, all of a sudden, the ultraviolet makes a comeback, and it sort of becomes a somewhat more normal-looking continuum from a quasar. And so what we think is happening is that the BAL outflow is dusty. And so we can't see into it when we get too deep into the ultraviolet, but we see it in the optical and near ultraviolet. And so that's why the BAL absorption has disappeared in the far ultraviolet spectrum. And yet continuum sneaks through because there's some kind of patchiness or some way that the ultraviolet light from the central engine is able to sneak out and evade this dusty screen. Now, that one is not necessarily misty. We also looked at another quasar. We were actually working on a whole bunch of these BAL quasars. And in this one, we were studying it because it had the usual famous big, fat, highly ionized BAL outflows. And it was quite ordinary in 2011. And when we looked again to monitor whether there were changes in the high ion BALs, we found that thousands of new absorption lines had appeared in the spectrum. including many iron 2 lines, Balmer absorption lines, helium 1 absorption lines. And it's important to note that the lower level in these absorption lines is not metastable. It's the lower level is connected to the ground state. So it should be easy to deplete the electrons from the lower level. And yet we see these things in absorption. So we modeled this, and basically it requires a huge density. We require a density of at least 10 to the 7 per cubic centimeter. And for the sodium, we actually found that we needed 10 to the 10 per cubic centimeter. Now, the stuff partially covers the flux source, and the partial covering depends on which ion we look at. It ranges from 0.04 for sodium to about 0.5 for the ultraviolet absorption lines. And so we can place constraints on it, so it's heterogeneous, and we can place constraints on its size. It's a pretty small thing. And so we thought, oh, this is cool. We'll just monitor it for years and then see how it changes. But it was not to be, because within a couple of years, it was gone again. So here we have something misty. You all might be saying, what the heck? Well, this isn't circumgalactic medium, but a lot of folks are interested in Agn feedback. And so here's an example of how we can start to look at the details of Agn feedback. And it's actually pretty interesting, even if the density is maybe 15 orders of magnitude higher than what we see in the CGM. Perhaps physics is not exactly the same, but whatever. I just like to talk about stuff that's fascinating. Let's keep going. So we see outflows in a lot of different situations. Here's Christy Tremonti's paper on the post-starburst galaxies, and she found magnesium-2 and these things moving at 1,000 to 2,000 kilometers per second, looking down the barrel. So the limitation of this was that you couldn't decide if it was just nuclear stuff or it had a more kiloparsec galactic scale. Sometimes, and this is happening more, the emission is seen with IFUs on large scales. Here's Rupke's beautiful paper showing oxygen-2 emission extending over 100 kiloparsecs, but often the densities are low and we don't know what's going on galactic and circumgalactic scales. So this is where quasar absorption systems become rather handy, because absorption is extremely sensitive when we can see that low density stuff way out and even into the intergalactic medium. So I'd like to make a few comments about a survey that I've been leading for a few years called the Cost Absorption Survey of Baryon Harbors, or COSBA. And the idea of this was to access all of the wonderful diagnostics that nature provided, but then quite mischievously hid in the deep ultraviolet. So there are all kinds of resonance transitions of all kinds of metals and ions, but most of them are in the far ultraviolet, below 912 angstroms, where we can't see them in the interstellar medium because of the hydrogen. But the trick to play is that if we look at a redshifted absorption system, then all this stuff gets redshifted into the observable band. So we've been working on this, and we detect all things we'd hope to detect. Some of them are in quasar outflow type stuff, and some of them are in foreground circumgalactic halos. We looked at 9 quasars with redshifts ranging from 0.9 to 1.5, signal noise 20 to 50 per resol. Cost gives us, 15, 20 kilometers per second resolution. We also got near ultraviolet spectra with COS and STIS. That's very important for line identifications, and often the oxygen 6 is redshifted into that band. And we obtained Keck high-res shell spectra. So the data look like this, and I hope you can see this. Normally, we're kind of stuck working with these species. Maybe we got silicon-2 and carbon-2, silicon-4 and carbon-4. It's kind of meager. But as we go deeper into the ultraviolet, we see that more and more ions and species are detected. These are all lines that are detected in a single absorption system in the spectrum of this quasar, PG 1630 plus 377. I think I've identified more than 8,000 lines in this single spectrum from the COSBA survey. So I think this is a wonderful archive for quasar absorption line people to use for years and years to come. I don't know, I think we've written a dozen papers or something that use these data, and we're continuing to work on it as hard as we can. You get often Lyman limit systems, you get coverage of the Lyman series, so you can get excellent H1 measurements in addition to the metals. It's really very powerful data. So what do we learn? I don't know why it sometimes stops advancing. Here we are. So we're also doing a Galaxy Redshift survey, much like what we heard about last week. And Prochaska has led this part along with Jess Work, our host, and many other people. Christopher Wilmer played an important role here, Joe Burchett. I mean, lots of folks have been helping out with this survey. So here we see the different galaxy redshifts with the impact parameter and the redshift along the x-axis. We also adopted a wedding cake strategy. We used the hectospect with its 300 fibers to get the brighter, lower redshift stuff. We use Sloan, of course, and then we use Demos on Keck to go deeper and narrower. And I think we got something like 5,900 galaxy redshifts at this point, and that's published Prochaska et al. 2019. So we can make statements about the O6 covering fraction, extending to very large impact parameters. We measured the O6 galaxy cross-correlation function. So there's a lot of information on how O6 absorbers cluster with galaxies. So I'm not going to spend too much time on that paper. I see time is marching on. I want to make a few more comments. We also provided the first survey of neonate absorption in Circum Galactic halos. So this is a paper that was led by Joe Burchett. And what we found is that when we have a galaxy close to the sightline at a redshift that brings neonate into our bandpass, we typically do detect neonate, at least within 1 or 2 virial radii. At larger impact parameters, we don't detect neonate. So the neonate seems to have a similar behavior to oxygen 6 and other ions that we know and love. This is not all of our neonate detections. This is just the neonate that's affiliated with galaxies. So this is a paper also came out in 2019. Supposedly it's an AppJ letter, but it seems to be 40 or 50 pages long somehow, so go and take a look at it. There's a lot of information in this AppJ letter. Joe Burchett is very good at writing AppJ letters that are far, far longer than they're supposed to be. So you talk to him about how you do that trick. I don't quite get it. My AppJ letters have always been 4 pages, Joe. All right, well, anyway, there's something interesting about this COSBA data. So here's an example. Here's one of the galaxies. We've got a spectroscopic redshift. It's 100 kiloparsecs from the quasar and projection. We see all kinds of lines, so it's great. We've got the H1 Lyman series lines. We've got neonate, sulfur 5, sulfur 4, sulfur 3, carbon 4, carbon 3, nitrogen 4, nitrogen 3, all these different ions that we'd hoped to find. And here are the ionization potentials for these things. It's really weird. You need say 50 eV to get rid of some of the lower ionization stages. You need 207 eV to make neonate, and yet these things are lined up beautifully. Here's the oxygen 6. I should probably just have this one figure in here. Anyway, if we look at these apparent column density profiles again, you see weird, just weird. The centroids and the line widths to whatever you can get with 15 kilometers per second resolution, which is a few kilometers per second, seem to be the same for things ranging from H1 to oxygen 3 to nitrogen 4, sulfur 5, and neon 8. We talked last week about whether the stuff is turbulently broadened, whatever that means, or thermally broadened. In this case, it's really hard it's not thermally broadened because you can look at things with different masses and they seem to have the same line widths. So what's going on? Here's another example that I'd like to show. Actually, my collaborators take bets on how long it will be for me to actually put this slide in because I always show it, but it never gets old. Just doesn't. Actually, I'm I'm working on some malware code. What I intend to do is set up this malware so that all astronomy talks will show this slide at some random time. So if you see this slide pop into your talk bizarrely, well, you'll know what happened, and just don't tell the FBI. Anyway, this one, here's the quasar, and Jane Charlton and Chris Churchill and their group have worked on this too with ground-based data. There's Galaxy about 70 kiloparsecs from the sight line. It seems to be a face-on galaxy. I don't know if you would go so far to say it's a spiral galaxy, but it sure looks like it's face-on. It has magnesium-2 absorption spread over 1,500 kilometers per second. So some of this stuff is probably escaping. It's quite different from what we heard about last week. But again, that's just magnesium-2. It's hard to work with that. Maybe just to sort of be speculative, maybe this is some kind of outflow, and on one side we happen to intercept the outflow where there's more stuff happening. On the other side, maybe we just nip off a bit more boring region, so we only see a little bit of the absorption. Even if you just focus on this part, it's probably got some escaping stuff in it. Now, here's the great part. Oh, that's annoying. That figure is not supposed to be in front. Well, it's fine. Here's the Lyman series lines, flux below the Lyman series. We've got excellent H1 constraints, and we see all these different metals. Oh, there we go. And they're all lined up. It's just nuts. The centroids and the line widths are very similar for things ranging from magnesium to up to Neonate. And so I'm just going to zip through this. We did some goofy thin shell model and came up with masses and outflow rates, and they're sort of interesting. I don't know how much stock to put in that model, and it's not really what I want to talk about, but I'll just flash those numbers up. It's probably an interesting outflow. But here's another one of these plots again, and just looking at different things compared to carbon-2, you see this extraordinary correspondence. The Keck magnesium-2 data has higher spectral resolution, but you can see the same features, recalling the discussion at the beginning of this talk, in the higher resolution data. So this is another, I think, important question for theorists. How on earth do we get these really disparate ionization stages to line up and track each other so precisely at these high velocities over a large velocity range? And you might accuse me of oh no, I'm missing a slide again. No way. I'm not sure what happened. Well, it's fine. You might accuse me of cherry picking the COSBA data and only showing the juicy examples, but it's actually not the case. This is very commonly observed in COSBA data, where if we look at something like carbon 4, H1, oxygen 4, and oxygen 6, we find they're beautifully lined up. Now, sometimes the line widths are different, but the centroids often are extraordinarily well aligned. But we should recall my little goofy lecture at the beginning. That doesn't mean that these things are co-spatial. In fact, thank you, Jess, they're probably not co-spatial, and I think the phase structure, the component structure, is just lost at cost resolution. But clearly, there's a relationship. That's the point I've been trying to make all these years, and understanding that relationship is important. And well, I don't know, maybe it's cloud shattering, maybe it's precipitation, maybe it's cooled gas that forms in the outflows. There's lots of great theorists here who can talk about these things, and so I just want to put the question out there. Now, I know I have to finish up, so let me just quickly advertise a paper that a graduate student working with me has just finished, which is really the only way to handle all these different ions with this unresolved and undistinguishable phase structure, I think, which is to take a Bayesian approach and just explore parameter space, probably with forward modeling if you can computationally hack it, and see what the constraints on the parameters are in that way. So Carl's put out this paper, and it's on AstroPH. We're going to hear more about this, I think, from Jane tomorrow. Her team has also done similar work, and there's also, let me advertise one of these videos. So there's a lot of information. So I'm not going to get into this in too much detail, and I'm out of time anyway. But there's a number of important priors and different parameters that we can explore. We can explore the, the density, the relative abundances that were discussed. We can add hot gas. We can do a lot of different things. One of the important priors I should mention is we put a prior on the cloud size. That's partly motivated by Michael Rauch's great work from years ago, showing that the things like carbon-4 are just not that big. So I'm not, I should say, compelled by models that require a very large, very metal enriched cloud. We can vary the shape of the UV flux field, lots of things. So let me show you some results. So for the oxygen 6, the Bayesian models really prefer a hot phase. And oh, by the way, we can put in multiple phases. We find a single phase just doesn't hack it. That's no surprise, but well, it's valid, it's helpful to show. You can rule out a single phase. Typically, we require at least 3 phases. And for oxygen 6 and neonate, the models tend to prefer hot gas. The models also tend to prefer an ionizing flux field that is softer and brighter than Hart and Maddow. And this is maybe what people wanted me to say most of all. I've sort of waited until the last possible moment, which is that we can look at the pressures in these different phases with all these different ions and metals, and we can ask, are these things in pressure balance? Do they have the same pressure and therefore seem like they might be in thermal pressure equilibrium, or do they have very different pressures? And this is a problem that Jess raised with her big cost halos paper from 2014, where she showed that the pressures are much lower than what you might expect from, say, the Mahler and Bullock model. So we even put in a prior to try to force the models to find pressure equilibrium. And here's what we found. Oh, I can't believe it. I don't know what's going on here. Well, I'll just tell you. The answer is, if we only allow photoionized phases, then we cannot find pressure equilibrium typically. And that's shown in this top panel. And it's no surprise, the highly ionized gas has to have a low density. There's not that many ionizing flux photons that can make oxygen 6. So the density has to be low. But the temperature is more or less the same. It's photoionized. So the oxygen 6 phase has a low pressure, but the more low ionization phases have higher pressure. So they're not in pressure equilibrium. But if we allow some sort of heating that makes some of the phases hotter, then we can find pressure equilibrium solutions. I should say thermal pressure equilibrium, because we don't put in non-thermal pressure sources. So let me skip ahead. I'll just quickly show something I think I've shown everyone before. With this high resolution spectroscopy with STIS, we can also look at the oxygen 6 absorbers that are redshifted, and we find that they too resolve into multiple components. And this is bad news. The components are narrow, and so the gas is cool. We can put an upper limit on the temperature. And so for this one, the upper limits are 20,000 and 10,000 Kelvin. So we shouldn't have any oxygen 6 there if it's collisionally ionized. So it sort of runs against what the Bayesian studies seem to indicate. Now, some people will argue that this is photoionized. I don't think it is. It's just, you have to have these big absorbers. That doesn't work for me. I think maybe there's some physics that's missing. I think, maybe the stuff cools more rapidly than it recombines, and it's just in an over-ionized state. So that's another question for theorists. So let me go ahead and put up some sort of goofy conclusions, and I will say thank you once again for your time and for the opportunity to participate in this wonderful workshop.